Hello. So in this lecture we will discuss goal of this lecture is to discuss Dirac spinors and the four component notation. So this four component notation is more usual in the textbooks. So let's first ask what is a Dirac spinor. So it's basically just a left-handed spinner with and a right-handed spinner. Dirac spinner is same as a left-handed spinner plus a right-handed spinner. So in the representation theoretic language, this is half comma 0 plus, not product, plus 0 comma half. So typically a Dirac spinor is written in this way. Psi alpha dot. It's a four component spinor. So for example, this is the left-handed one. And this is the right-handed one. Okay, so then with this, this is also there is also something called gamma matrices. So gamma matrices, gamma mu is same as 0 gamma mu alpha dot, sorry, sigma mu alpha dot sigma bar mu alpha dot alpha 0. So four of them, four matrices, each of them are 4 by 4. Okay, and you can check that the gamma matrices, so this is actually called the wild representation of gamma matrices. Okay, so more generally, I mean, you can check for this particular representation, but more abstract definition of gamma matrices is that the anti-commutation of two gamma matrices follows this relation. So this is the identity matrix. And this is the metric tensor. So this is eta mu nu is diagonal minus 1 1 1 1. Okay, and this anti-commutation relation is known as Clifford algebra. Okay. Now from these matrices and from these things you can define one matrix which is called gamma 5, which is I gamma 0, gamma 1, gamma 2, gamma 3. So this is definition, and you can check that this anti-commutes with all the gamma matrices. So anti-commutes with the gamma matrices. Okay, and this is often called the chirality matrix. The reason for this is that in this particular representation you can check that gamma 5 is simply a 4 dimensional matrix, but 2 by 2 block diagonal of this form. And then basically we can define a projection operators. So projection operators, so this is called the left-handed projection operator, and this is called the right-handed projection operator. Okay, so this projects to left-handed spinors. This projects to right-handed spinors. Okay, so this is the way typically people introduce the two component spinner, the left-handed spinner and the right-handed spinner, starting from the Dirac spinners. Okay, we have taken a different route. We have first defined the two component spinner, then we have done the 4 component spinner. But usually we'll see in the textbook, the thing that is done is they start from the Dirac spinner and then define the 2 component spinners. So let's now ask that how does the Dirac spinner transform under Lorentz transformation? So in order to do that, first we define the Lorentz generators. So they are defined in the following way. Okay, so this means that J, I, these are the rotation generators. And you can explicitly check in this case that Jij just simply becomes half epsilon ijk sigma k 0 sigma k 0. Okay. So these are the rotation generators. Rotation generators in this panel. Okay, and similarly we can also define the boost generators. So the boost generators are J0I, and again you can use this formula to show that this thing just simply becomes minus I by 2 sigma I 0 0 minus sigma I. Okay, so these are the boost generators. Okay. So then in general a finite Lorentz transformation, so these are the generators of the infinitesimal transformation. The finite Lorentz transformation is given by the exponential map. So these are the parameters of the Lorentz transformation, and a finite Lorentz transformation is then given by exponential I omega mu nu j mu nu. Okay, for example, a finite boost along ith direction is exponential. If you put all these things, you will get it is exponential I by 2 zeta sigma I 0 0 sigma I, and that just becomes simply cos hyperbolic zeta by 2 times identity plus sine hyperbolic zeta by 2 sigma I. So this is the finite boost generators. Now we'll briefly again discuss now the discrete symmetries. In the 4-component notation. So let's first discuss reflection. And to be more precise, let's discuss reflection along x directions. So in reflection, if we want to discuss reflection along x direction, then that means that in terms of the space-time coordinate, the space-time coordinates will go to. So this implies in terms of the gamma matrices, okay. So let's now say that the reflection under reflection the gamma matrices more generally just go to like Rx gamma mu Rx inverse. Okay. If that is the case, then from this it follows that Rx should be just simply product of gamma x and gamma 5. And in general, if you want to do reflection along ith direction, it will be some gamma I times gamma 5. Okay, so this is how the gamma matrix is transformed. And let's now talk about how the spinors transform. So under reflection, a spinor, Dirac spinor, so the Dirac, how does it Dirac, because yeah, so under reflection the Dirac spinor just simply goes to Ri times this. Okay, so if we just know the reflections, we can figure out the action of parity, because parity is simply just 3 reflections. Okay, and actually you can check that Rx, Ry, Rz, these things commute, so it doesn't matter at what order we can do this. So this is the action of parity. Now you see that we already discussed it, but let's just see that what happens to gamma 5. So under gamma 5 also goes to, let's say under reflection, Ri gamma 5 R inverse, and you put this explicit formula, it flips this. So this implies reflection and hence parity flips chirality. Okay, so this already, which means that left-handed spinor goes to right-handed spinor, and vice versa. So this is the way we saw that how the left-handed spinor go to right-handed spinor and right-handed spinor go to left-handed spinor. If we do reflections, I mean, and hence also if we do parity. Okay. Let's now discuss time reversal. So time reversal is a linear. We know that time reversal is a anti-linear, anti-unitary operator. Which means that it can be written as a so time reversal can be written as some RT times K, where K is complex conjugation matrix, complex conjugation operator, and this is some linear unitary operator. Now one thing I want to stress is that the explicit form of RT the action of RT is basis dependent. So in our particular case, you can check that in our particular case RT is gamma 1, gamma 3. Okay. In our particular case, gamma 1 RT just becomes gamma 1 times gamma 3. Then important thing is in this case is that in this case T square is equal to, which is same as RT times K and RT times K. This just becomes then, because gamma 1 gamma 3 are real in our basis, which is becomes RT square times K square, and this is just minus 1. So time reversal squares to minus 1 for Dirac fermion. Okay, so let's now discuss some symmetries. Axial and vector symmetries. So if you remember that Dirac spinner was just a combination of two. So Dirac spinner was a combination of a left-handed spinner and a right-handed spinner, right? And we remember that the left-handed spinner and the right-handed spinner, they were independent, and they were both of them complex. So which means that we can rotate them, right? So this was a rotation in the two component, this is the phase rotation in the two component language. So now in the four component language, there is again a two parameter rotation. So one choice is if theta 1 is equal to theta 2, then psi just goes to this, okay, and this is called vector rotation. This is called not vector rotation, it's called vector u1. The reason for calling it vector u1 will become later when we construct the action. For the time being, just take it to be a name. And similarly in the four component notation, we can take theta 1 to be minus theta 2 equal to theta a, and then in the four component notation this just becomes exponential I theta a gamma 5 acting on psi, and this is called axial rotation. Okay, so when so this is usually called u1v and this is called u1a. So when we try to construct the action later, you will see that this plays a very important role, and I mean this gives rise to symmetry and conserved quantities. But basically this is just in the two component notation, this is the simple thing. This is just how the two component spinors transform under if we try to rotate them. Great. Now then let's talk about the kinetic term. So the kinetic term in the 4-component notation takes the simple form psi bar I gamma mu del mu psi, and this thing is often written as del slash psi. So this is same as psi bar I del slash psi. Okay. So this is the mass. This is the kinetic term. Now about the mass term. The mass term, the Dirac mass term, we discussed the Dirac mass term in length in details. The Dirac mass term in this basis just simply becomes m psi bar psi. I mean, if you remember Dirac mass term, how we got the Dirac mass term? Let's remind you. Dirac mass term is simply mass term for two spinners, two left-handed spinners. Let's say left-handed. Such that the mass is same for both. Okay, and that mass term in the 4-component notation just simply becomes m psi bar psi. Okay, and then you remember that the mass term had a U1 symmetry. So in this case, the U1 symmetry is the vector U1, but also note this is not invariant on the axial U1. Okay, this is consistent because we already discussed that the Dirac mass term has only one U1 symmetry. So here also in the 4-component notation we also expect it to be only one U1 symmetry, not more generally. So this is the thing that happens in this case. Okay, so if we try to perform an axial rotation, then the mass term simply changes. The mass term becomes m1 psi bar psi plus m2 psi bar gamma 5, I m2 psi bar gamma 5 psi, such that m1 square plus m2 square was my original m square. Okay, so the bottom line is that more generally one can write down such a mass term, but this is same as Dirac mass term because of field redefinition. Okay, because of the field redefinition, psi goes to exponential I theta. So that's why whenever we usually do 4-component notation, usually we never write down such a mass term. Usually we do not write down such a mass term. But basically the reason is that we can always transform this mass term into that more canonical mass term, the Dirac mass term, just by a field redefinition symmetry. However, in a more general case, the more general case discussion is given in the note, that if you have n Dirac fermions, then what is allowed and can you always write it in terms of Dirac mass term or not, that thing is given in the note. So I encourage you to go through that, and the statement is that in a free theory, for n Dirac fermion, the mass term can always be written as mi psi bar I psi. Okay, so there is no off diagonal term, there is no phase, there is no gamma 5 thing, because even if you write that, there is always some field redefinition symmetry using which I can always bring it to the canonical mass term. Okay, so this concludes our discussion of the action in the 4 component notation. Next time we will discuss Dirac equation and its solution and various physical consequences.